As you design and write assembler code, there will be many times when you'll notice a need to perform a program function over and over. In assembler, looping is a way to do this. A loop is just a sequence of instructions. The loop starts with a labeled statement. It contains instructions to perform the loop's basic function, and it ends with an instruction that, depending upon a certain condition, either branches back to the start of the loop or falls through to the next instruction in the program, the first instruction outside of the loop. In this video, you'll learn program techniques for looping. We will look at a situation where looping might be useful. And then we will look at assembler language instructions that can help you create a loop in your code. Let's look at a situation where a loop might be handy. It's a situation dealing with a table of data, sales data. It could be sales data by the day or the week or the month. Right now, let's say it's sales data by quarter, to keep the example simple. Our job is to create a segment of code to add up the sales data for the 4 quarters of the year and store the result in a field called sum. A table is just an area of storage with a name and a certain structure. The name of this table is sales table. It consists of a series of half words next to each other in memory. We'll assume that the quarterly figures are already in the table. Here's a section of code that could do that job. We'll assume register 4 has been cleared to 0. We add the first value, then the next half word, then the third half word, and finally the fourth half word. Then we store the total into the field named sum. But if you had a 50-entry table, would you use this type of structure? What if you had a 500-entry table? Part of the challenge of programming is recognizing places in your code where you can save yourself work by making the code more flexible and efficient. This is one of those places. Let's see how we can make this code more efficient and flexible by using looping techniques. What do we want here? We want a loop, a segment of code that will select a table entry, add it to the accumulator, and then repeat the same thing with the next table entry. It will exit from the loop at the proper time. Using instructions you've already learned, you could set up a loop that counted the number of values you added and then branched out of the loop after you added 4 values. But System 370 assembler language provides you with 4 special instructions especially for loops. Branch on count, branch on count register, branch on index low or equal, and branch on index high. We'll look at each of them in this video. Our first loop involves branch on count. This instruction gives you a way to count the number of branches you make and then to move on. It uses a register as a counter, in this case, register 5. We set up the counter register, register 5, with a number, 4 in our example. 4 is the number of times we want to go through our loop. Each time the branch on count instruction is executed, it decrements the value in the register by 1. As long as the value is not 0, the instruction branches to the location named by the second operand, loop. When the value becomes 0, the instruction does not branch. It falls through instead. In effect, the instruction counts the number of times we go through the loop. Let's take a closer look at our example. We know that we want to add 4 values. So we load the counting register, register 5, with the number 4. Then we enter the loop. We add the first value in the table into our accumulator register, register 4. Then we take the table entry index, initialized to 0, and add 2, so that the next time we will access the second half-word entry in our table. Then we come to the branch on count. What's in register 5 right now? 4. As the branch on count instruction executes, it first subtracts 1 from the value in register 5. Then the instruction compares the value in register 5 to 0. If the value is not equal to 0, the branch takes place. We have 3 in register 5, so right now we go back to loop. We add the second half-word entry into our accumulator register. Then we bump up the table entry index again to get ready for the next time through the loop. Now we're at the branch on count again. It subtracts 1 from register 5, so 3 becomes 2. That's still not equal to 0, so we branch back to loop again. We add the third table entry, increment the table entry index, and branch one more time. The value in register 5 is 1 after the branch instruction is executed. Once more, add, increment, and come to the branch instruction. We've added all 4 numbers now. Will we exit from the loop? The value in register 5 is 1, but the instruction decrements that to 0, checks it, and decides no more branches. Execution falls through to the next instruction, where we store the accumulator register into a field called sum. So the branch on count instruction gives us a way to control the number of times we execute a loop. It uses a counter, register 5 in this example. It modified or decremented that counter by -1 each time the instruction was executed. And when the counter reached its lower limit of 0, we didn't branch. A counter, a modifier, and a limit. Watch for these loop control elements in the other examples we will see. Our next looping instruction is branch on count register. It works much like branch on count. One difference is that the second operand is a register, not a label. When it branches, branch on count register branches to the address in that second register. So before we start the loop, we load the address of loop into register 6. From there on, the instruction works very much like branch on count. When we exit from the loop, we fall through to the following instruction. There is one special use for branch on count register. It will let you subtract 1 from a register without branching, if you wish. Code the second operand as register 0, and the instruction ignores that branch operand while still subtracting 1 from the register you name in the first operand. The next looping instruction we want to look at is branch on index low or equal. Branch on index low or equal can make your code even more efficient than branch on count, and it's more flexible. However, there's a trade-off. It's more complex to understand and use. Here's the format of the branch on index low or equal instruction. The first operand is an index. We'll use it to access the proper place in our sales table. The second operand is an increment or modifier. We'll use it to bump up the index each time through our loop. The third operand is the branch address, just like in branch on count. There's also a hidden operand here. When the second operand is an even-numbered register, it specifies a pair of registers. So besides the even-numbered register 6, the increment, we have register 7 to work with. We use register 7 as a compare, an upper limit to our loop. Let's see how it works. Here's the loop as we will use it. Our add instruction takes the half word pointed to by this address. That's sales table indexed by register 5. So if register 5 contains 0, we get the first value in sales table. If register 5 contains 2, we get the second value in sales table. But we have some housekeeping to do before we start the loop. We'll use a load multiple instruction to initialize the registers. Register 4 is our accumulator. We set that to 0. Register 5 is our index. We need to set it to 0 so that the add half-word instruction accesses the beginning of the sales table to start. Register 6 is our increment. The branch on index instruction will add this increment to our index register. Since the entries in our sales table are half-word entries, we want the increment value to be 2. And don't forget register 7. That will be the upper limit for determining when we exit the loop. Branch on index will compare the value in register 5, our index register, to the value in register 7, our limit register. That means that we want a value in register 7 that will end the loop when we've added all of the numbers. That will be after 4 loops, or 4 increments to the index register, when the register equals 8. So when the index register is greater than 6, we want to exit the loop. We set the limit in register 7 to 6. Let's see what happens. Here's how things look before we enter the loop. The first instruction takes the half word at the beginning of sales table. Because register 5 contains 0, there's no offset. It adds that first value from sales table into register 4, which becomes 1,000. Now, let's consider the branch on index low or equal. This instruction adds the contents of register 6 to register 5. Register 6 is our increment value, 2. Register 5 is our index for the table offset. The sales table, modified by this offset, now points to sales table plus 2. The branch on index low or equal instruction compares register 5 to register 7. It branches if register 5 is less than or equal to register 7. So we branch back to loop. This time the table pointer is the beginning address of sales table indexed by register 5, or sales table plus 2. We add the second half word into our accumulator. Register 4 now contains 4,000. How about the branch on index low or equal instruction? First, it adds the contents of register 6 to register 5 to give 4 in register 5. That will be our sales table offset the next time through the loop. Then the branch on index low or equal instruction compares the contents of register 5 and register 7. Register 5 is still low, so we branch back to loop. Our sales table pointer is now the beginning address of sales table plus 4. We add the third half word to the accumulator. The branch on index low or equal instruction adds register 6 to register 5 again, giving 6 in register 5. It compares register 5 and register 7. They are equal. Our instruction is a branch on low or equal, so we branch back to loop again. This time we add the value at sales table plus 6 to our accumulator. That's the fourth and last value in the table. Will we branch again or fall through? The branch on index low or equal instruction adds the contents of register 6 to register 5 again. The instruction compares registers 5 and 7. Is register 5 low or equal? Not anymore. The index register is high. That means we fall through instead of branching back to loop. You can see that the branch on index low or equal instruction is flexible. Depending on your needs, you can set up the instruction in a variety of ways to accomplish your loop. Branch on index high gives you that same kind of flexibility. It has a similar format, and you use branch on index high in similar situations as branch on index low or equal. It has a different condition for branching. Let's use it to add the numbers from our sales table. Suppose there might be times when we didn't want to execute the loop at all. We could use a branch on index high to do that. Here's a situation like that. The branch on index high comes as the first instruction in the loop. We're looking at the loop after the loop instruction has been executed 4 times. This is the 5th time for the branch on index high instruction. The instruction adds the contents of register 6, the increment register, to the contents of register 5, the index register. Then it compares register 5 to register 7, the limit register. If the compare is high, If register 5 is higher than register 7, the instruction branches. This way, the loop wouldn't be executed at all. Of course, you could set up a similar type of structure with the branch on index low or equal. We've been using one version of the branch on index instructions. That's where the second operand is an even register. When you write the instruction like that, you get a pair of registers, one for the increment and one for the limit. When you specify an odd register number as the second operand in the branch on index instruction, there is no hidden second register for the limiting value. So here, register 7 is both the increment value and the limiting value. When this instruction is executed, the contents of register 7 are added to the contents of register 5. Then the instruction compares register 5 to register 7. If register 5 is low or equal, the instruction branches to loop. If register 5 is high, no branch occurs. Let's look at a different example of branch on index low or equal, an example you might want to keep in mind. The purpose of this code is to add the corresponding entries in Table 1 and Table 2 to Table 3. We use the same index register to access all three tables. Register 5 is the index register. Register 6 is the increment. And register 7 is the limit. Register 4 is a work register. Registers 5, 6, and 7 are all initialized with the load multiple instruction. The first instruction in the loop loads the first entry of Table 3 into Register 4, our work register. The second instruction adds the first half word of Table 1 to the contents of Register 4. The third instruction adds the first half word of Table 2 to the work register. So we've added the first entries from Table 1 and Table 2 to the first entry in Table 3. The results are in Register 4. The store half word instruction stores the total back into the first entry of Table 3. Then, branch on index low or equal increments the index, compares the index to the limit, and branches back to add the remaining values. This is an example of how the branch on index instructions can drastically reduce the amount of code you need to write in certain situations. Let's take a look at the instructions you've seen. Branch on count uses a register as a counter. It automatically decrements the counter each time through a loop. When the counter is 0, it branches to the address you specify as the second operand. Branch on count register is similar. It also uses a register as a counter, but the second operand is also a register. It contains your branch address. Branch on index low or equal is the third instruction you saw. It gives you one operand as an index and another operand as an increment to that index. If you specify the even-odd pair for the second operand, you also get a separate register for the limit to your loop. The last operand is the branch address. Finally, branch on index high is similar to branch on index low or equal. There's an operand for the index, the increment, the limit, and the branch address. Please turn to Mini Course 11 in your PRG and read the summary. Then complete exercise 11.1.